Hi, this is Roger from Kanka Labs, today with episode 4 of the much too long running video series about selecting a better multimeter. So after we finished the basic measurement functions like voltage, current, resistance and VA or power, let's deal today with, on the one side, component testing like diodes, Zener diodes or transistors, and the temperature measurement capability of the multimeters. But before that, we take a look at a not so often used feature, that is a frequency and duty cycle measurement. But because I've already connected a function generator to it, we'll, as the first point, take a look at the usability of the bar graph. Now you can see down on the left the signal that goes into the multimeter, and that is basically a 1.5 volt DC voltage, and superimposed is a sine wave with 500 millivolts peak voltage. And at the moment you can see it has 10 Hertz frequency. Now for me, the only use that I can think of is of the bar graph is that it can show you if you have a varying DC voltage, and the voltage we are now putting at the input is just that, a DC voltage that is basically varying between 1.25 volts and 1.75 volts, and the average is of course 1.5 volts, and all at the moment display 1.5 volts, and at 10 Hertz frequency of the superimposed sine wave we can see absolutely no movement in the bar graph. And let's turn down the frequency a bit to see when the bar graph starts to show us that we have a variation. So at 7 Hertz we can see the displayed DC voltage starts to change a little bit, and it's not a stable value. And the EV block multimeter just barely shows a little bit flickering segment in the bar graph, just as well as the X-Tech, but at 7 Hertz. Now you mostly have something like 50 Hertz superimposed. And now at 5 Hertz, this becomes more obvious. And for me, this is basically a useless or the bar graph is basically a useless function if it only shows you a variation in your measured DC voltage at 5 Hertz or lower. And there's a much easier way to check if you have a superimposed AC voltage or a varying DC voltage. You just go to AC mode and you see we have 0.17 volts AC voltage superimposed. Let's do the same here, and 0.16 and something. And here we also can go into AC mode and see 1.7 and something. So that is a much better check to see if you have any superimposed AC voltages than just relying on the bar graph. So in fact, I can't remember any situation where I've even watched or remarked the bar graph. And so the bar graph is more a gimmick that was introduced somewhere in the 1980s or that time about. And I find it's only a gimmick, and for me it has absolutely no usage, no matter what they claim here, how fast the update rate is, etc. So let's go over to the frequency measurement, which was quite a novel feature here for this old Metex from the 1980s. And basically you have two kinds of frequency measuring mode. One is what is called the logic level mode. This is basically for square waves measuring at your digital circuitry. And so let's change the setup a little bit just to see how useful this frequency measurement feature really is for a multimeter instead of an oscilloscope or a true frequency counter. So let's start with a rigorous test. We are having a square wave, as you can see on the secondary image, with a 20% duty cycle. The frequency at the moment is 100 kilohertz. And we have slightly above 2 volts peak amplitude. and the Metex has no problem with that. You can see the accuracy is not that good. This is not a hardware or digital frequency counting device, but as I understand it from the schematics, it has a frequency to voltage converter inside, and so it basically measures the voltage of the converter, and that means, of course, there you have inaccuracies, especially if we have such a non-symmetrical square wave. The X-Tech has no problem with that, and we can change from free. And by the way, here we have 6 digits, and you can see 5 of them are correct. Here, I don't know if you can see it, the Rigol scope also has a dedicated hardware counter inside, and it displays the exact value, 100.000 kilohertz. And here we have 99.9992, so 5 significant digits, and that's better than what the specs say. And at the moment, the EEV block multimeter doesn't display anything. Before that, I can show you the duty cycle measurement. The X-Tech displays correctly 19.43%, so I cannot decide why it's not exactly 20. Is this from the function generator, which of course also has a limited accuracy, or is it due to the multimeter? Anyway, we're quite near to the exact value. And why doesn't the EV block display anything? Well, in the manual they state that the multimeter needs 2.5 volts RMS at the input to display anything. That's a bit strange, because the signal that is now fed into the multimeter is a typical signal you can get when measuring digital circuitry, that it's non-symmetrical and has not 50% duty cycle, and modern digital logic today is usually much lower than 5 volt. The next step would be 3.3 volt, but there are also a lot of modern digital circuitry with 2.5 or 2.2 volts, and you always lose a little bit of amplitude. So 2 volts peak should still be in the range that a good multimeter can measure, and now it becomes stranger again. When we go to line level measurement, for that we simply go to AC mode, and on the secondary display now we can see that more or less, except for the least significant digit, 99.99 kilohertz. So what is here basically dedicated to so-called line level measurement in the AC mode gives a correct display, but when we go to the dedicated hertz measurement we don't get it, because apparently the amplitude and or the duty cycle, which both affect the RMS voltage. So let's first of all, for a check, change the duty cycle to 50%. You can directly dial that in. And now suddenly we get a halfway, oh no, it's stabilized correctly, except again for the least significant digits. So we have 4 significant digits, while the X-Tech gives 5 significant digits. So simply by changing the duty cycle and thereby giving a higher RMS voltage, it is able to measure down to 2 volts. Now we go back to 20% duty cycle and rise up the amplitude and see in Hertz mode now again it shows 0. And let's see at which amplitude we get a correct result. There it starts, but still a wrong value. So 2.4 volt. Okay, there it sets in. So it really needs not 2.5 volt RMS, but it needs a peak voltage of 2.5 volts. And then the duty cycle can be away from 50%. And now what's quite nice, we not only can display the duty cycle, but also the period of the signal. And that's quite handy, because quite often you're not interested in the frequency but in the period, and doing a 1/x division in your head is quite difficult if it comes to non-round values, and picking up a calculator is sometimes not possible. So it's quite nice that this is a simple calculation in the microcontroller. Sorry that the X-Tech that they didn't think of that. It could be that the newer model of this one, which has some additional features, but basically has the same setup and ranges, etc., that this can also do period. And if we press the mode button once again, we get the duty cycle, and let's see, now we're at what? 49%? That is a bit, not a bit, that is totally out. Strange. So let's raise the amplitude still more. 3 volts. So now we're getting nearer, but it takes a lot of amplitude rise to get near to 20%. We're already at 4 volts peak, so near TTL level. And now we're at still 10% out of the correct value, and also TTL, even if it has nominal 5 volts peak, you quite often have some losses of voltage due to parasitic capacitance, etc. So let's go to 5 volt and see, yeah, we're still a bit out. So we have a resolution of 0.1% in the duty cycle, but 100 kilohertz is not a very unusual signal. Even for PWM modulation, 100 kilohertz is not such a high frequency, so I would expect this to be a little bit more accurate. Look at the X-Tech, we're now much better than 1% here with 5 volt peak. So, and sorryly, when we go back to AC mode, we only can display the frequency, not by changing the mode. We only change from AC to true RMS AC plus DC, but we cannot change the secondary display. Why doesn't it? No, we're in DC. We cannot change the secondary display to duty cycle or period. So this could also be changed in the firmware, that we could better make use of the secondary display, because the multimeter has the capability in AC mode to display correct values, but not in the dedicated Hertz mode. So let's go back with the amplitude again to, let's say, 3.3 to 3 volts, but see if at a lower frequency, for example 10 kilohertz, if there we get a more correct. No, the duty cycle is really, concerning the accuracy, is quite bad, I must admit. This could be much better, because this is basically measured digitally inside. So no, we're out of the specs here, even at a 10 kilohertz signal. This is not very reliable, and anyway, if you will never use your multimeter to measure frequency or duty cycle if you have a DSO, a digital oscilloscope, at hand. I've used the frequency measurement function very, very seldomly, but if it is implemented, it should give halfway decent results, as we can see even with the 6-digit mode here with the X-Tech, which is quite nice in that way. And you can see it's only about 0.2% of the true, or 0.3% of the true value. So let's see what is the upper frequency range. Of course, here with the little METEX, it's obviously 200 kilohertz. Let's see at this amplitude what the others tell us. With 200 kilohertz, okay, there we still get a correct result, even with a 20% duty cycle. Let's crank this up to 500 kilohertz. Yep, still good. 1 megahertz. So here we are, that is the maximum range is now over. So 900 kilohertz, no. So 800 kilohertz seems to be the limit for the X-Tech, which is already quite high. And let's see, yeah, and 1 megahertz. So they are both between 900 kilohertz and 1 megahertz, where they level off, and so we can be quite happy with the frequency range having 1 megahertz frequency counter implemented. Let's see if this improves here with the X-Tech at 900 kilohertz if we go back to 50% with the duty cycle. Yeah, there we're spot on, or nearly spot on. So there remains one thing in the so-called, the other mode, the so-called line measurement mode. What is the minimum level that the multimeter meets and what is the maximum frequency there? So for line level measurements we have to change here to AC mode, and also in the X-Tech here the METEX makes no difference. It always gives either correct values or it's over range. So let's for that case change to a sine signal. Let's go and take the offset off. So now with the EEV block we only have the secondary display with a 4-digit, but that is enough because usually when you're measuring in the audio frequency range it's not so important to have 6, 7 or 8 digits of resolution and accuracy. It doesn't matter if your audio signal has 15.01 or 15.02 kilohertz. So let's go down at 100 kilohertz, which is a reasonably higher end for audio or general purpose frequency measurement. So let's go down with the amplitude and see when. And at 1 volt peak, the X-Tech already has quit, while the EV block is still good. So the X-Tech apparently either needs a higher amplitude. So I had to make a little break and consult the manual and play around a little bit to find the issue with the X-Tech. Against your intuition, when you're in volt AC mode, which is the natural setting for measuring frequency, then it has no problem going to higher frequencies, but the amplitude, because we're only in volts and we're not having millivolts, the amplitude is limited to around 2 volts. If we go below that, then the multimeter doesn't trigger anymore its frequency measuring functionality. But if we go to DC mode or even millivolts DC and then to the Hertz mode, here in volts mode we still don't get a display. But if we go to millivolts and then again to Hertz mode, no problem. So, and then now we can go down. So we have again the high accuracy, even with 6 digits. Let's see if the EV block also displays frequency in the millivolt mode. It should be. Yes, it does. So let's do a comparison side by side. And now we go down with the voltage at 100 kilohertz. First to 100 millivolts. 100 millivolt at 100 kilohertz is apparently too low, while here even the old METEX has no problems with, so it starts to trigger at 200, so between 200 and 300 millivolts. Let's see if this gets better at lower frequencies. Let's go down to 20 kilohertz. Yeah, 20 kilohertz seems to be no problem at all. And now let's lower the amplitude further down. So at 100 millivolt we are again having a problem with the X-Tech, while the other twos are still displaying the right frequency. So we can take this out of the comparison and now further go down until finally we get no triggering 50 millivolts and still within Specs, both show 20 kilohertz. 10 millivolts, peak, no problem at all. 5, 4. Now the Metex has quit. Let's see where that was. Yeah, the limit is around 20 millivolts, peak, or in other words 6.7 millivolts RMS for a sine signal. So that is still quite good. 6.7 millivolts is usually you're doing those measurements with audio equipment, and there you mostly have much higher voltages than 6.7 volts. Now let's see where finally the 121 GW will give up. So I can't get any lower, but there it has quit. Where was that? At 7 millivolts peak. That's 2.2 millivolts RMS, so that's a really good result. Final verdict concerning the frequency and duty cycle measurement. The X-Tech is much better, especially with digital signals. It can measure without any problem the correct duty cycle. It measures the correct frequency even with very low or very high duty cycles, where the EV block just quits quite early. And on the other hand, measuring sine signals or normal audio kind of signals, the sensitivity of the EV block is extremely good, while here the X-Tech is quitting and the Metex is still quite good with, what did we have, 20 millivolts peak, where it starts to measure. So however old this is, and even if it's not a true digital counter, but a frequency to voltage converter and then measuring the voltage, this is still quite good. But to be honest, and as I already told you, I never really used this function actively because I always have a scope near hand, and I barely remember any situation where I used the multimeter to measure frequencies. Okay, if you don't have a DSO or an analog scope with you, it's better than nothing. But I think the frequency measurement and duty cycle is perhaps okay for quickly measuring PWM signals. But the duty cycle measurement is nearly the only thing that makes sense to me, which is, in my view, a really useful features for real test work. Anyway, if you don't have a DSO, better than nothing to have frequency, duty cycle, and here additionally the recalculation of the period time of your signal. So that was it for that part, and now let's go over to capacitors, diodes, Zener diodes, transistors, and temperature measurement features and comparison.